Hey guys, this is Space Train, your daily express till the edge of the space, and today we will talk about Einstein's theory of relativity. Grab your tickets and let's go. Our train will explore the whole universe to find answers to some important questions. So make sure you have subscribed to get unlimited pass on our expedition. Relativity, wide-ranging physical theories formed by the German-born physicist Albert Einstein. With his theories of special relativity, 1905, and general relativity, 1915, Einstein overthrew many assumptions underlying earlier physical theories, redefining in the process the fundamental concepts of space, time, matter, energy, and gravity. Along with quantum mechanics, relativity is central to modern physics. In particular, relativity provides the basis for understanding cosmic processes and the geometry of the universe itself. What is special relativity? The theory is based on two key concepts. First, the natural world allows no privileged frames of reference. As long as an object is moving in a straight line at a constant speed, that is, with no acceleration, the laws of physics are the same for everyone. It's a bit like when you look out a train window and see an adjacent train appear to move, but is it moving, or are you? It can be hard to tell. Einstein recognized that if the motion is perfectly uniform, it's literally impossible to tell, and identified this as a central principle of physics. Second, light travels at an unvarying speed of 186,000 miles a second. No matter how fast an observer is moving or how fast a light-emitting object is moving, a measurement of the speed of light always yields the same result. Starting from these two postulates, Einstein showed that space and time are intertwined in ways the scientists had never previously realized. Through a series of thought experiments, Einstein demonstrated that the consequences of special relativity are often counterintuitive, even startling. If you're zooming along in a rocket and pass a friend in an identical but slower-moving rocket, for example, you'll see that your friend's watch is ticking along more slowly than yours. Physicists call this time dilation. What's more, your friend's rocket will appear shorter than your own. If your rocket speeds up, your mass and that of the rocket will increase. The faster you go, the heavier things become and the more your rocket will resist your efforts to make it go faster. Einstein showed that nothing that has a mass can ever reach the speed of light. Another consequence of special relativity is that matter and energy are interchangeable via the famous equation E equals mc squared, in which E stands for energy, m for mass, and c squared the speed of light multiplied by itself. Because the speed of light is such a big number, even a tiny amount of mass is equivalent to, and can be converted into, a very large amount of energy. That's why atomic and hydrogen bombs are so powerful. What is general relativity? Essentially, it's a theory of gravity. The basic idea is that instead of being an invisible force that attracts objects to one another, gravity is a curving or warping of space. The more massive an object, the more it warps the space around it. For example, the sun is massive enough to warp space across our solar system, a bit like the way a heavy ball resting on a rubber sheet warps the sheet. As a result, Earth and the other planets move in curved paths, orbits, around it. This warping also affects measurements of time. We tend to think of time as ticking away at a steady rate. But just as gravity can stretch or warp space, it can also dilate time. If your friend climbs to the top of a mountain, you'll see his clock ticking faster compared to yours. Another friend, at the bottom of a valley, will have a slower ticking clock, because of the difference in the strength of gravity at each place. Subsequent experiments proved that this indeed happens. Special relativity is ultimately a set of equations that relate the way things look in one frame of reference to how they look in another, the stretching of time and space, and the increase in mass. The equations involve nothing more complicated than high school math. General relativity is more complicated. Its field equations describe the relationship between mass and the curvature of space and dilation of time, and are typically taught in graduate-level university physics courses. Relativity is one of the most famous scientific theories of the 20th century, but how well does it explain the things we see in our daily lives? Here are some examples. 1. Electromagnets. Magnetism is a relativistic effect, and if you use electricity you can thank relativity for the fact that generators work at all. If you take a loop of wire and move it through a magnetic field, you generate an electric current. The charged particles in the wire are affected by the changing magnetic field, which forces some of them to move and creates the current. But now, picture the wire at rest and imagine the magnet is moving. In this case, the charged particles in the wire, the electrons and protons, aren't moving anymore, so the magnetic field shouldn't be affecting them. But it does, and a current still flows. This shows that there is no privileged frame of reference. Thomas More, a professor of physics at Pomona College in Claremont, California, uses the principle of relativity to demonstrate why Faraday's law, which states that a changing magnetic field creates an electric current, is true. Since this is the core principle behind transformers and electric generators, anyone who uses electricity is experiencing the effects of relativity, Moore said. Electromagnets work via relativity as well. When a direct current, Sn, of electric charge flows through a wire, electrons are drifting through the material. Ordinarily the wire would seem electrically neutral, with no net positive or negative charge. That's a consequence of having about the same number of protons, positive charges, and electrons, negative charges. But, if you put another wire next to it with a Sn current, the wires attract or repel each other, depending on which direction the current is moving. 2. Global Positioning System. In order for your car's GPS navigation to function as accurately as it does, satellites have to take relativistic effects into account. This is because even though satellites aren't moving at anything close to the speed of light, they are still going pretty fast. The satellites are also sending signals to ground stations on Earth. These stations, and the GPS unit in your car, are all experiencing higher accelerations due to gravity than the satellites in orbit. 3. Your old TV. Just a few years ago most televisions and monitors had cathode ray tube screens. A cathode ray tube works by firing electrons at a phosphor surface with a big magnet. Each electron makes a lighted pixel when it hits the back of the screen. The electrons fired out to make the picture move at up to 30% the speed of light. Relativistic effects are noticeable, and when manufacturers shaped the magnets, they had to take those effects into account. 4. Light. If Isaac Newton had been right in assuming that there is an absolute rest frame, we would have to come up with a different explanation for light, because it wouldn't happen at all. Not only would magnetism not exist but light would also not exist, because relativity requires that changes in an electromagnetic field move at a finite speed instead of instantaneously, Moore, of Pomona College, said. If relativity did not enforce this requirement, changes in electric fields would be communicated instantaneously, instead of through electromagnetic waves, and both magnetism and light would be unnecessary. Now you can see why we consider Albert Einstein as a goat. There are lots of questions left, so don't space out, and leave some space in your brain for answers. I hope you enjoyed this video. If you want to see more, subscribe and click the bell button to get notifications on our latest videos. If you are still here, grab your knowledge and get out of my train.